So, we discussed the geometry of how the vectors are using the normal equation of the hyperplane, and the next step would be to going into the details of the construction of this optimal hyperplane towards this linear machine. Okay. So, now let us begin our discussions here. Now, g of x is the discriminant boundary, and I mentioned to you from the geometry in the last lecture that a vector x can be split into the vector which is lying in the plane, that is in the direction of the hyperplane, and a component which is normal to the hyperplane, and x is given by xp plus r times w naught upon the norm of w naught. Now, let us go into the details. The discriminant function, when it is evaluated on the xp component which is in the direction of the hyperplane, that is equal to 0 because xp lies on the discriminant boundary, right. This is very important. So, xp lies on the discriminant boundary. So, therefore, g evaluated on xp is 0, but g is an affine map because g of x in general is given by w naught transpose x plus bias, is very important. So, note it is w transpose x plus b. Because of this it is an affine map, right. There is a bias b there. If the bias is not there, it would be a linear map, right. So, you have to pay attention. If b is equal to 0, it becomes a linear map, and if b is not equal to 0, in general it is an affine map. Okay. Now, let us evaluate g on the point x. So, g of x is g of xp plus r times w naught upon norm of w naught. If it is a linear map, if the bias is not there, then I could say g of xp plus some other vector is g of xp plus g of r times w naught upon norm w naught. But since it is an affine map, I have to evaluate g on this composite vector which has both these components. So, let us plug this in directly. So, g of x is w transpose x plus b. So, what I do is I plug in x taking this form xp plus r times w naught upon norm of w naught. So, I get w naught. So, I put this w naught here to be consistent. So, it is w naught transpose xp plus r times w naught upon norm w naught plus this bias b naught. So, I repeat again. So, g of xp plus r times w naught upon norm w naught is w naught transposed of xp plus r times w naught upon norm w naught plus I add this bias which is b naught. So, what I do is I split this into two parts again. I group w naught xp plus b naught into one part, the other is w naught transposed times this r times w naught upon norm w naught. So, rearranging this slightly. So, whatever I have here within this green brace, here I just expand this out. So, I get w naught transpose xp plus b naught plus this other term, but w naught transpose xp plus bias b naught is nothing but g of xp, and that happens to be 0 because it lies on the discriminant boundary, plus this other term w naught transpose r times w naught upon norm w naught. But r is just a scalar because it is an algebraic distance. So, you pull this r out. So, I have w naught transpose times w naught upon norm of w naught, but w naught transpose times W naught is nothing but norm of W naught square, right. So, this quantity here is nothing but norm of W naught square, and this is basically 0, g of x p is 0. So, therefore, I just get g of x to be just r times norm of W naught. So, therefore, the algebraic distance r can be computed as g of x upon norm of W naught. So, that is a relationship between the algebraic distance g of x and W naught, right. This is an important simplification. Now, the distance from the origin to the hyperplane can be straightforwardly evaluated to be b naught upon norm of W naught, right. And if b naught happens to be greater than 0, then the origin is on the positive side of the hyperplane. If b naught is less than 0, the origin is on the negative side of the hyperplane, and if b naught equal to 0, then the optimum hyperplane, this is hyperplane, I said it is hyperplane here. So, let us make the small typo corrected. So, if b naught equals to 0, then the optimum hyperplane passes through the origin. So, this is an important geometric field to this problem. Now, our training set comprises of this set of points xi di, where di is a label which is +1 or -1, and xi are the set of points from I equals 1 to n. Now, let us see the geometry of this problem. So, we said g of x, which is W naught x plus b naught, that is the optimum hyperplane, right. Our optimum hyperplane has this equation W naught transpose x plus b naught, right. If it is equal to 0, then this is the equation of this plane. Now, if W naught transpose xi plus b naught, if it is greater than or equal to 1, then we associate the label di equal to +1, and W naught transpose xi plus b naught, if it is less than or equal to 1, then the label di equal to -1. So, when it is equal right, when it is equal to 1, we do not know whether it is label +1 or -1, it is equally likely. But there are particular data points, this is a very important detail, there are particular data points xi di for which these equations are satisfied with equality, and those are called our support vectors. That is, an xi of s, I indicate in the superscript the variable s, indicating this as the support vector, and these are vectors that satisfy this rule with equality. But what is the geometric field for this problem? Let us assume that they are linearly separable. That means there is this gap between these classes, and this gap is not 0, right. There is a gap which is not 0, where you can clearly separate the vectors or the samples in the two classes. So, let us imagine we have these x's which is belonging to one class, and we have the circles that belong to another class, and support vectors are those vectors that are lying on those boundaries which are indicated by these bold blue lines. They are lying on each of those boundaries, and there is a hyperplane W naught that separate these support vectors. And you do not have to confuse the equation of the bold line with the dotted line, right. That the dotted line has the parameters W naught and B naught, and these bold lines have some plane equation that satisfies equal to 0, right. Let us not confuse ourselves with that. And those support vectors that satisfy this relation W naught transpose xi plus B naught to be greater than 1, or I mean with equality, right, which is equal to 1, they are called the support vectors. They are lying on the the critical side of the boundary. Now consider a support vector x of s, right. I have deliberately ignored the subscript I. So G of xs can be evaluated as W naught transpose x of s plus bias B naught. So this is going to be equal to -1 if the associated label is a -1, and it is a +1 if the associated label is a +1. And the algebraic distance from the support vector x to the optimum hyperplane is given by this quantity r, which is equal to G of x upon W naught, where x happens to be the support vector, and this is 1 upon norm W naught if the associated label is a +1, and it is -1 upon norm W naught if the label happens to be a -1, right, because if it is lying on one side it is +1, on the other side it is -1, and the corresponding algebraic distance has the sign +1 or -1 scaled with 1 upon norm of W naught. Now if we know the algebraic distance, we can say that the margin of separation for the optimum hyperplane is 2 times r, where r is the algebraic distance, right, and I want to maximize the margin of separation, right. Just recall this diagram again. This is our gap, and I want to maximize this gap, and if W naught transpose x plus B naught equal to 0 is this equation of the hyperplane, when I evaluate I get plus r here for this and then minus r for the other, right. I have this this margin of separation. Now r is 1 upon norm of W naught, and I want to maximize this margin of separation, because the bigger the margin the better it is. Why should I maximize the margin of separation? Imagine you have a noise cloud. So let us say you had some x's here, some circles here possibly, right. If I have noise, some of these points can come in this region and some of these circles can go back into this region, right. So I have these blue circles and I have these blue crosses. If I have noise, then I can have the circles to be on this side and the crosses to get back on the other side of this hyperplane. So in some sense I am sort of accounting for some signal to noise ratio metric in this scenario. That is, I want to maximize the margin of separation, because if I maximize the margin of separation during my training set over my training set, then if the test set has points which are lying on the other side of this boundary, in some sense I am optimized over the signal to noise ratio. So maximizing rho would be minimizing the Euclidean norm of this vector W naught, right, because they have a reciprocal relationship. maximizing the margin of separation rho is minimizing the Euclidean norm of the vector W naught. But you have to bear in mind that in the optimization problem that we are trying to solve, over all the points in the training set we are maximizing the margin of separation. That still cannot give us a hyperplane which in some sense has a unique direction or whatever. We are minimizing the Euclidean norm, and this Euclidean norm is basically a scalar quantity, and vectors with different orientation can have the same Euclidean norm. So, I can also have a hyperplane which could be this. Suppose I give you some set of points, let us say these crosses are here and these circles are here, right. I can have a margin, let us fix it like this. So, I will go with my convention of having dotted lines for the hyperplane and solid line for these two classes, for lines which separate the two classes, and critically lying providing you this margin here, right. This margin is rho in this case, but I can also have, I will indicate in red, possible lines like this in some orientation, which can also give me the same margin rho measured in this sense, and an orientation which is slightly different, right, assuming that I can get linear separability with these red dotted lines. So, what this really means is this problem of optimization is optimizing over the maximum margin of separation, which leads itself to minimizing the Euclidean norm of the vector W naught, but not necessarily the direction or orientation of W naught, right. That is an important detail here. But this is better than the perceptron where we started off with, because we did not have an objective metric to maximize or minimize something that can drive us to a solution which is unique with respect to that metric, right. So, this is an important detail that is a take home message from this lecture. So, we will stop here and then we will set up the optimization problem, and then we will try to solve this problem in the context of primal dual problem setup for the SVM.